So far, Bobby let us know about the freedom of particle motion as a key factor for predicting the direction of a spontaneous process, and that an increase in particle arrangements or microstates will increase the ways to disperse energy in a system. Well, we keep seeking guidance from Bobby, folks, and learn about the familiar thermodynamic concept that is directly related to the number of ways the energy of a system can be dispersed, of course, through its motion of its particles. And that is entropy, symbolized as capital S. Okay? We may have heard of entropy as a measure of the randomness or disorder in a system, which it still is. And of course, it increases as things become more disordered due to particle arrangement. That's the same entropy, folks. But now we can add a layer of information and say, if entropy is associated with particle arrangement, and particle arrangement is all about microstates, then the number of microstates in a system is related to entropy. And our mathematician and physicist, Ludwig Boltzmann, is to thank for our understanding of the relationship between entropy and the number of microstates, or W. And how does he do this? By way of an expression called the Boltzmann equation. And the Boltzmann equation is going to state that entropy is equal to the Boltzmann constant times the natural log of W. Now, W is the number of microstates, and the Boltzmann constant is going to be really the universal gas constant divided by Avogadro's number, okay? And so when you divide these two numbers, you get 1.38 times 10 to the negative 23 joules per Kelvin. And of course, capital S is going to be entropy. The number of microstates have no units. And so, in order to figure out the units of entropy itself, we have to focus on the units of the Boltzmann constant. The Boltzmann constant have units of joules per Kelvin. Therefore, entropy will also have units of joules per Kelvin. Since we can directly relate entropy and W, or the number of microstates, with this expression, we can say that a system with fewer microstates is going to have a lower entropy, and a system with more microstates is going to have higher entropy, okay? And we can also go further and say all spontaneous endothermic processes are then going to exhibit an increase in entropy. Bobby then says entropy, like enthalpy and internal energy, is a state function. Therefore, the change in entropy of a system is simply going to be the difference between its final and initial values. And we can write the expression as delta S of the system is equal to entropy final minus entropy initial. And as with any state function, the sign of delta S of the system can be positive or negative. So if delta S of the system is greater than 0, it's going to be positive, and you have an increase in entropy. If delta S of the system is less than 0, it's negative, and you have a decrease in entropy. Let's get a couple of examples of when we have an increase in entropy or a positive delta S of the system. So one quick example would be sublimation of dry ice. You're going from solid CO2 to gaseous CO2. And because you're going from less freedom of motion for the particles to an increase in freedom of motion for the particles, you are then going to increase the microstates. If you increase the microstates, you're then going to increase entropy. Another example will be if you have one molecule of gas that's broken into two molecules of gas. Because you increase the number of molecules of gas, that means you're going to increase motion and therefore increase entropy. Some examples of when delta S of the system is less than 0 or a decrease in entropy quickly would be like condensation. You're going from water vapor to liquid water. Again, you're going from a higher microstates to fewer possible motions and therefore fewer microstates. What's that going to lead to? A decrease in entropy. Another example will be if you have, say, 2 moles of gas that will react to form a solid. You're going from gaseous particles, which have more freedom of motion, to a solid particles, which have less freedom of motion. Less freedom of motion is going to decrease entropy. Next, Bobby states that there are 2 ways to calculate an entropy change, and of course, both ways are going to yield the same result. One approach is based on counting the number of microstates in a system, and the other is based on the heat absorbed or released by the system. And of course, our system is going to be chemical reactions, right? We're going to examine both ways, and we're going to do it with the system that is 1 mole of a gas, and that gas is going to be expanding from 1 liter to 2 liters. And of course, that gas also needs to be behaving ideally. And so our example is going to be 1 mole of neon gas. It's going to be behaving ideally. So we're going to have a temperature of 298 Kelvin, and it's going to be expanding from 1 liter to 2 liters. And we're going to be using this as the catalyst for all of our 2 examples to see how we can approach calculating these delta S of the system. Since there are 2 ways, let's start with the number of possible particle arrangements or microstates, and let's start with that way of calculating delta S of the system. Okay, folks? So here we have the spontaneous expansion of a neon gas. There are going to be 2 flasks. 1 flask is evacuated, and then 1 flask has 1 mole of neon. As you can see, they're connected by a stopcock here. Now, when we open the stopcock, the gas is going to expand until each flask contains 0.5 moles of neon. So we start off 1 mole here. We're going to open the stopcock, and as you can see, both are going to have 0.5 moles and 0.5 moles. But the question still remains, why? Well, opening the stopcock is going to increase volume, which increases the number of translational kinetic energy levels the particles can occupy as they move to more locations. Now you have to be like, hold up, what is kinetic translational energy levels, right? This just means how many different energy levels the particles can have when they move around in a straight line and go to different places. So that translational or energy is going to be going from point A to point B in a straight line, okay, folks? And so, of course, kinetic is the energy of movement, and so there's the energy of movement in that straight line. And we're saying that we're increasing these energy levels, so we're going to be increasing the ability for these particles that then move into more of these energy levels as the stopcock opens. And why would this happen as well? Because we know that these type of processes, these spontaneous processes, are going to go towards higher entropy, okay? So if we're increasing these kinetic translational energy levels, that means we are increasing the number of microstates. If we're increasing the number of microstates, then we are increasing what? Entropy. I then say increase S, increase W, and all because you increase the volume and increase the energy levels. All right, folks? The goal is that you are using your flashcard moments to make sure you stop and consolidate this information the best way possible. If you're having any issues connecting or layering information, the issue could be is that you don't have a true voice for even something like this. So I would stop and either write smaller notes for myself, write the expression that's necessary, and then pull out the most important information. That is the goal of the notes. That's the reason why I try to have you get down to only writing a page of notes, because you're getting down to the nitty-gritty, or I would say the meat and potatoes of the information. We can also present the same idea. An increase in microstates is an increase in entropy due to a spontaneous expansion of a gas with particles on energy levels in a box, like we see here, of changeable volume. And so, for example, if I were to open the stopcock, then the energy levels are going to increase because, again, we are increasing those translational kinetic energy levels. And, of course, the volume is going to increase as well. And then because of this increase in microstates, we're going to have an increase in entropy. So here we have our expandable box. Each line is going to represent an energy level. When we open that stopcock, you see we have an increase in these number of lines. And you also see that the width of the box is also increased as well because there was an increase in volume. You also have these 21 particles that are then going to be arranged into their own microstates. And of course, you can go further and arrange those microstates into macrostates, right? But that's not what we're seeing here. We're just seeing the particles arranged into microstates. Next, we can represent that same idea. Increase in microstates means an increase in entropy with a 2-flask system. So we have a 2-flask system here. One side of the flask, as we saw before, is going to have a certain amount of particles. For example, our particles are going to be atoms in this example here. And then we're going to have another portion of the flask is going to be evacuated. Of course, we have a stopcock represented in the middle. When that stopcock opens, then that means we're going to have an increase in volume, increase in translational kinetic energy levels, and then, of course, an increase in microstates. So each of these here are going to represent an individual microstate. We're not talking about macrostates here, folks, only microstates, okay? And also, when we open the stopcock and we allow that increase in volume, okay, the relative number of microstates is going to be 2 raised to a power of n. And n is going to be based on the number of particles. For us, that number of particles are going to be atoms. So when you have one atom in this 2-flash system, you open the stopcock, you're going to have 2 raised to the power of 1, which equals 2 microstates, okay? And if you have 2 atoms, you're going to be 2 raised to the power of 2, which is going to be 4 microstates. If you have 3 atoms, 2 raised to the power of 3, which is going to be 8 microstates, okay? And what do these numbers really mean? It means that the final microstate for, say, this one atom system here is 2 times as large as the initial microstate value, okay? So our final microstate value is higher than our initial. We see that here with the 3-atom particle system. So when we say 2 to the 3, we have 8 microstates versus initially 1 microstate. So increasing the volume creates 2 to the n more microstates. And we also know microstate number, or W, is related to entropy based on the Boltzmann equation like we saw before. And since entropy is a state function, we can also treat the number of microstates, or W, as a state function. Why? Again, due to the relationship in the Boltzmann equation, which that they're directly related to one another. And so now all we have to do is focus on the final number of microstates and the initial number of microstates. And when we do this, this link allows us to calculate the ratio between W final and W initial. And that ratio is going to influence the likelihood of particles being in different states, meaning the likelihood of them being in the final state or the final microstates versus the likelihood of them being in the initial microstates. And of course, this ratio is going to make it easier for us to analyze any entropy change. So I can write W final divided by W initial to, again, calculate my ratio here. Of course, let's use an example by actually calculating this ratio. Let's go ahead and use the 3-atom system here. So if we are going to have 8 microstates in the final divided by 1 microstate initially, that's simply going to equal 8, right? We can also write 8 as 2 raised to a power of 3. This 2 raised to a power of 3 can also represent the 2 raised to a power of 3 atoms in the system, okay? And so we can also say that our ratio for W final over W initial is equal to 2 raised to the power of n. And n is just going to be the number of particles in a system. So if we had 10 atoms in our system, it'll be 2 raised to a power of 10, which is equal to 1,024. And so the ratio of W final divided by W initial will equal 1,024. Of course, for us, because we're in chemistry, we like to focus on the mole. So let's say we had 6.022 times 10 to the 23 atoms particles in our systems, or 1 mole of the atoms. Then we can say we have 2 raised to a power of 6.022 times 10 to the 23 number of microstates, which is a huge number. A number so large is going to be very difficult to type in your calculator. But we can say that our ratio of W final and W initial is equal to 2 raised to a power of Avogadro's number. A lot of times you'll see Avogadro's number simply symbolized as N subscript A, okay? Let me go ahead and write that again. And what does this ratio, again, really represent? It's telling us that in the final microstate number is 2 raised to a power of Avogadro's number times more than the number of microstates initially. So that is a huge increase of entropy because you have a huge increase in the number of microstates there. Okay, folks? And of course, now that we have this number here, we're going to go forward and calculate delta S of the system. Okay, and we can actually use this W ratio to solve for delta S of the system, and I will show you how. First, we have our delta S of the system. Now, delta S of the system is going to equal to entropy final minus entropy initial. We know the Boltzmann equation, so S is equal to K natural log of W. So we can plug in K natural log of W final and K natural log of W initial for our S values here. So therefore, our delta S of the system is equal to K natural log of W final minus K natural log of W initial. From the properties of logarithms, we know that natural log of A minus natural log of B can also be written as natural log of A divided by B. So we can say our delta S of the system is equal to K natural log of W final divided by W initial, just based on the expression here. And guess what, folks? We already know what our ratio of W final divided by W initial is for when we have 1 mole of atoms, right? And so, or particles in our system. And this is going to be 2 raised to Avogadro's number. And so now we can plug this entire thing into our overall equation. And we get delta S of the system is equal to K natural log of 2 raised to a power of 6.022 times 10 to the 23. Now, anytime you have, we can use another property of log, right? And anytime you have natural log of A raised to anything, you can actually rewrite it as Y natural log of A. And so that's exactly what we're going to do, so we can go ahead and solve for delta S of the system. So now we're going to bring down this 6.022 and to the front of the natural log of 2 and rewrite the expression because they're equal to one another. So we can write delta S of the system is equal to K times 6.022 times 10 to the 23 multiplied by natural log of 2. That means we're going to now plug in all of our numbers because we know the Boltzmann constant as 1.38 times 10 to the negative 23. We're going to multiply that by Avogadro's number, and then I plugged in natural log of 2 in my calculator and got 0.693. So therefore, delta S of the system is equal to 5.76 joules per Kelvin. And this is our first way of calculating delta S of the system. Bobby then reminds us that the last approach to quantify entropy change is based on the heat absorbed or released by the system. Let's look at the change in entropy for a gas that is heated and does work on the surroundings. This means that when an overall gas is heated, its internal energy is going to increase and it does work on the surroundings. And so since work is being done by the system, work is going to be a negative value. And the type of work that's being done by the system might mean it might expand or push against something, okay? And the change in entropy is going to be a way of understanding how the energy and particles are dispersed or spread out within the system as it heats up and performs that work, okay, folks? And this approach uses one relationship here. And that relationship is delta S of the system is equal to Q rev divided by T. Now we know delta S of the system is going to be the change in entropy of the system. We know T is going to stand for temperature. Now Q is going to be our heat, and then rev is going to mean a reversible process. So Q is usually going to be our heat absorbed for our example, and then rev again, it means reversible process that happens in very tiny steps, therefore keeping the system in balance and allowing the change's direction to be easily reversed with, again, very tiny adjustments. And so what we're going to do is simulate a reversible process and then continue our calculation. So to simulate a reversible process, we are going to use a piston cylinder assembly, okay? And this piston cylinder assembly is also going to have a heat reservoir to maintain that constant temperature of 298 Kelvin since we are dealing with an ideal gas, okay, folks? Remember, our examples are always dealing with 1 mole of neon gas that is ideal. That's going to be expanding from 1 liter to 2 liters. So right now, we have our cylinder. It has a piston. And of course, we are going to have 1 liter volume here. And that piston is also going to have the weight of a beaker of sand attached to it. Again, helping us maintain that 1 liter. Within this 1 liter, we're going to have 1 moles of neon gas. Essentially, a sample of 1 mole of neon gas is confined to a volume of 1 liter by the pressure of a beaker of sand on the piston. So if we remove 1 single grain of sand with a pair of tweezers, that's going to actually represent that tiny or minuscule decrease in pressure just by removing 1 single grain, okay? That tiny minuscule decrease in pressure is going to then cause the gas to expand a tiny or minuscule amount due to a tiny increase in volume, right? Thereby raising the piston and doing work on the surroundings. When work is done by the system, work is in a negative value. And when the gas does work on its surroundings, by moving the piston or increasing the volume by that tiny little bit amount, the system is going to absorb a tiny increment of heat. Where is it going to absorb the heat from? The heat reservoir, okay? That means we're going to get a positive Q value. So work is going to be done by the system and be negative, and our Q value is going to be positive. With each grain of sand removed, the expanding gas absorbs another tiny increment of heat. And this process simulates a reversible process, or specifically reversible expansion. The question then becomes how? How is it reversible? Well, the way we can make it reversible is simply by replacing the grain of sand. So whatever we took out, we're going to put back in. So if you're going to be adding your sand grains back in, you're going to be increasing pressure a tiny amount, therefore decreasing volume by a tiny amount, and work is going to be done by the surroundings in order to push the piston down by a tiny amount to prove that we are decreasing volume. And what's also going to happen, as you compress the gas, you're going to release a tiny quantity of heat back to the heat reservoir. Okay, but let's go ahead and continue what we were doing before and remove grains of sand to continue this nearly reversible expansion to that 2-liter mark. Remember, our examples are going from 1 liter to 2 liters. So what we're going to be doing is removing sand grains until we get to 2 liters of expansion. We can then go further and use calculus to integrate the tiny increments of heat together and get a value for Q rev, okay? And that value is 1,718 joules. So if we have a value for Q rev and we know we are at 298 Kelvin as our temperature, we can go ahead and calculate delta S of the system. So using our equation for delta S of the system, I'm now going to plug in my values. So our Q rev value was 1718 joules divided by a temperature of 298 Kelvin. I get 5.76 joules per Kelvin. As you can see, this is the same value we obtained from counting the number of microstates as before. Now, knowing all of this, what can we now say about predicting spontaneous change? We can say that entropy plays a significant role in favoring spontaneous changes as the system moves towards a state with more energy and particle arrangements, but still not the whole story when it comes to predicting specifically spontaneous change. So we need to leave Bobby for now and get to making more connections with our own investigations back at the motel.